Alrighty, guys. Good morning, and welcome back in again today to year-long college algebra. Today, as a parent, I am out of the classroom. I've got a PD day that I've got to get off to in order to teach some of the Algebra 1 curriculum that we're working with. So I'm out of the office. You'll have a sub today. The good news is that you guys have a video lesson that's going to be pretty straightforward. There's not a whole lot of surprising material or anything that's going to be very new as far as like the big concepts, like how we're applying some of the stuff from earlier in the unit. We're kind of taking this idea of changing formats of quadratics, but we're also going to connect that up to what we already understand so far from Unit 1 about how to sketch graphs for these guys. And a lot of that's really going to revolve around this idea of transformations, but also maybe some new strategies when we don't have something in vertex form. As we settle in, please be sure to put your phone in the correct numbered slot over there by the phone caddy. The sub knows that you guys need to have your phones up during class, so unless you're taking pictures to submit the homework in like the last 5 to 10 minutes, you want to make sure that these are put away as we move into the lesson proper. Otherwise, though, I'm going to get you guys rolling here with a quick warm-up. Here, you're going to be given three functions, f of x, g of x, and h of x. They're all quadratics. Two of them are written in vertex form. F of x is what we refer to as the parent function. It's like the most basic pattern of behavior that a quadratic is going to have before you really tack on the different transformations and kind of mess with things and you go from there. So what I want you to do real fast is maybe construct a table of values for f of x so you can figure out what the sketch of this is going to look like by hand without using any technology. So without like Desmos or a graphing calculator, I want you to figure out what the graph of that parabola is going to be. And then I want you to identify the transformations that make f of x look more like g of x or h of x. And once you've got those, go ahead and maybe try and give a graph of those. Maybe on like a scratch piece of paper or like on a mini whiteboard just to kind of get the gears turning. I'll give you a minute to kind of mull it over. We'll bring it back together, get this knocked out, and then we'll launch right into it with some of the new notes for today. All right. So if we're taking a look at some of these functions, and in particular, we want to just start to explore like the basic pattern of behavior of what makes a quadratic. I always like to build a table of values for these, and just to sort of investigate before I think about transformations, just to get kind of the basic pattern of behavior that makes these unique and distinct from other families of functions that we've seen so far. I usually go with like kind of a standard spread of x values. I usually like to use negatives and positives. I'll go here from like maybe -3 to +3. I almost always include 0 because with a lot of these parent functions before transformations, it's going to give you a nice convenient output that you can get down quickly on the graph. So all I'm really doing is taking all of these inputs, plugging them into f of x to see what the corresponding output is. So for example, if I want x equals 0, I'm going to plug it in or substitute it into f of x to do f of 0 and see what I get as a result, which in this case is also 0. If x is equal to 1, I'll substitute that in and think about what 1 to the second is. That's just a 1. It gets more interesting the further out we go, though. For 2 to the second, that's 4. For 3 to the second, that's 9. Also note that in the negative direction, when you square a negative, because it's a negative times itself, that switches back to being positive. And that's what gives these quadratics this sort of U-shaped, parabolic, symmetric graph. So I'll take these values and jot them down on the coordinate grid over here to the right so we can get kind of like a better picture of how things are moving and changing. There's also some key features that I want to point out for this guy that are going to come in handy as we get a little bit further in our lesson today, talking a little bit about some of these new strategies we're going to develop to graph when we're not necessarily starting in vertex form. So this guy in red, this is our function for f of x. One thing I want you to notice is that as you increase x by 1 at a time, the pattern for change in the y values is not consistent. There is a pattern to it, but instead of going like +1, +1, +1, it's more like +1, +3, +5. And if you test x equals 4 and you get the output of 16, you see that the change there is like +7 in the y's. So the way that it's changing has a pattern to it, but it's not just plus the same number, like absolute value, right? It's a little different than that. And it's the same pattern as you go to either edge of the graph. Something else to notice is that if you take like this parabola and you cut it in half by putting a vertical line down the y-axis, also known as like this line x equals 0, you get this perfect like reflective symmetry. So with quadratics, we usually refer to this as like the axis of symmetry. This point here, that's the minimum of the graph, we often refer to as the vertex. And as you'll see, as soon as we start to introduce some of the transformations for g of x and h of x, that's why it's called vertex form, because it helps us navigate and figure out where this vertex has gone. But by default, it always starts with this coordinate 0, 0. So that's the basic pattern of behavior. I'm going to sort of clear some space here and start thinking maybe about the changes that are going to happen with g of x or with h of x. So with g of x, I might do this in a different color. I might go with this kind of like this nice dark blue color. I'm trying to spot the different transformations that have occurred and what they're going to do to the graph. If I see this plus 4 on the end of the function, I know that that's going to translate the graph up 4 units. And if I see this value here, x minus 3, I know that really that's going to go the opposite direction of what I might think it says in the x direction. It's actually going to go right 3 instead of left. That's the counterintuitive one. There's also this last part out in front. We have this a transformation of -2. This is kind of doing two things at once. It's going to reflect over the x-axis. So anything that was like right side up, I'm now going to use the pattern backwards, where I'm going to go upside down. It's also going to move twice as fast as usual if there's a 2 present instead of a 1. And if you're in doubt about why that works, go ahead and try building a table of values for like -2x squared, and you'll see what I mean about how the pattern goes twice as fast in like the negative direction. So putting all this together, I'm going to kind of clear some more space here. So I'm going to erase some of my notes for like the vertex and the axis of symmetry. I'm going to take my vertex first and foremost, and I'm going to take that and move it right 3 units and up 4 units. So now it's over here at this coordinate 3, 4. So I might say that that's like V, that's that location. Normally my pattern from there is that I go over and up 1. Here what I'm going to do is go over and down 2 in both directions. So we're moving a little faster than we usually would, and we're opening in the other direction. The next step in the process is once I go over 1, up 1 for the parent function, I usually go over and then up 3. I got to go twice as fast from these coordinates. So if I go right or left 1 from these 2 coordinates that I've created, I've got to go down 6 units instead of 3 units to get that to hit the right speed in this context. So I've still got a parabolic graph. It's still this sort of nice symmetric U shape, but it's upside down and it's a little skinnier because it's moving faster in the y direction than we had previously set up. What I want you to notice here, though, is that we still got an axis of symmetry and we've still got a vertex. So vertex form gets its name because it tells us where that vertex is at. The axis of symmetry, which I'll abbreviate as the AOS, you'll notice passes through that coordinate. So it's like this line x equals 3. Again, that's kind of neither here nor there for what we're doing right now. This will come in handy a little more as we get into today's lesson. And then finally, maybe on the last one here, which I'll do in like this dark green color, we've got h of x. If I see -6, I know that that's telling me I'm going down 6. If I see +4, normally +4 in the x direction makes me think I'm going right. I got to do the opposite here. So I got to say that this is actually left 4. This a value of 3 tells me that I'm moving up, but I'm moving up 3 times faster than usual than what the default pattern is going to say. So if I put all that together, that's going to help me get the graph of my function for this guy. All I'm really doing is just kind of following the directions. I start at 0, 0 with my vertex, but then I go left 4, and I go down 6, and this is now the new starting point for our parabolic graph. Normally, I go over 1, up 1, over 1, up 3, over 1, up 5, if I have an a term of 1. This guy's 3 times as fast as usual. So instead of over 1, up 1, I know that I'm going to go over 1, up 3. So I'm going to have this really narrow, skinny parabola, kind of in this lower left quadrant going up really, really fast. So now I've got to go over 1, up 3, but 3 times as fast. So to wrap this up, I'm going to go over and up 9 units. This thing's moving really, really quickly in the positive y direction. But again, I know where the vertex is at, and I know where that the axis of symmetry is passing through it. The other thing that I might note here is that I've got a couple of x-intercepts where I'm crossing the x-axis. That'll come into play when we start talking a little bit more about solving. For today, we might say is essentially that we're thinking about like the halfway point between them is where the axis of symmetry passes through. We'll kind of talk about that as we go, though. The vertex is at -4, comma -6. The axis of symmetry passes right through the middle. That's going to be the line x equals -4. Just a little practice to kind of review and recap some of the different ways that we worked with graphing when we're trying to do the whole thing by hand. So today, we're going to kind of revisit the skill of graphing, but we're going to do it in this new context where we're thinking about some of the different forms of equations that quadratics can come in. We're going to be working on graphing skills for when it's in standard, it's in vertex, or it's even in factored form. We're going to hit our first quiz when we come back on either the 24th or the 27th, depending on whether you're an A-day or a B-day student. Otherwise, though, we're moving right along into our Unit 3 material. This will be kind of like the first half of the quarter. This will probably take us most of the way into Thanksgiving break. Once we get closer to Thanksgiving break, we'll start thinking about wrapping this up and then hitting our last unit, which is going to take us into the final exam in December. So we're moving right along. We're working with quadratics. We're revisiting the skill of graphing. The thing that helps a lot with this is to know like what the basic pattern of behavior is for all quadratics, transformations or otherwise, simple or complicated. All quadratics, no matter what you do to them, are going to have this nice parabolic U-shaped graph. It comes from the fact that at its most basic definition, a quadratic has a variable squared somewhere in its problem. You might have an a term tacked onto it. You might have like a plus 5x and then a -6. It might be in vertex form, so it's like x minus 3 squared. But if you take all those different forms and condense them back down to standard form, you'll always have an x squared present. And that's what dictates the way that the graph has this shape. The pattern of behavior here is really important to memorize. If you start at the vertex, you go over, up 1, over, up 3, over, up 5, over, up 7, over, up 9. If you know that pattern, it's going to make it way easier to graph by hand if you don't have access to a graphing calculator or something like Desmos. We spent a lot of time practicing that back in Unit 1 and in Unit 2. It's going to come back today when we think about graphing with transformations, especially when we're thinking about vertex form. We've seen a lot of different parent functions and a lot of different families of functions. The one thing that's always consistent is that if you got A, H, and K, they do the same thing no matter what template you're working in. That can be exponential, logarithmic, could be rational, reciprocal, radical. They all do the same thing. So the good news is that if you're comfortable with how these different parameters are going to affect the graph, and you know the pattern for the parent function, the process for graphing these is almost always the same. We just got to kind of read off the transformations and work from there. The diagram that we saw back in the notes for 3.1, where we have the 3 different ways of experiencing a quadratic in its different formats and the ways to convert between them, that's still going to be helpful in the context of graphing. The reason that this is still useful is if you have, say, a quadratic in standard form and you want to graph that, it's not always the easiest thing to try and do in standard form itself. It might be easier maybe to complete the square to get it into vertex form so you can use transformations, but it's not necessarily the only way to do it. We're going to have multiple ways to skin the cat today when we're given these different quadratics. You may find like you have a preference for one method or another. Whichever works best for you, feel free to run it. I'm not going to be like a stickler where you got to know every single way to do it. If you're a big fan of completing the square to get into vertex form, by all means, knock yourself out. So let's take a look and kind of revisit how we might be able to graph when, say, you got something in vertex form. Here in the notes for 3.2, this is probably the most straightforward format in the sense that vertex form tells us by transformations where things are going to move compared to some kind of parent function. So again, I'll graph f of x equals x squared here in red. I've got a coordinate at the origin, 0, 0. I go over 1 and up 1, and then I go over 1, up 3 to get the next ones. And then from there, I'd go over 1 and up 5, and that would take me up to like a y value of 9, and I don't really have space for that. So if you find that you're kind of running out of room on the graph, you don't necessarily have to carry the pattern all the way out. So long as you get maybe some of the most important coordinates, like the vertex, maybe the first couple, just to get a good idea of the shape of the graph. It doesn't have to be perfect. If we start to introduce some transformations, all we're really doing is kind of revisiting the idea of how this is going to affect it in the same way that it does for every other pattern of functions. I know this plus 3 on the outside is that k term, so it's going to shift my graph up 3. If I see minus 1 inside parentheses, that's going to shift the graph right 1. And then I got this a term of negative 2. So that kind of does two things at once. It's going to flip the graph in its pattern of change upside down, but it's also going to take that pattern and make it twice as fast as usual. So if I've got my vertex at 0, 0, and I take it right 1 and up 3, that's where I'm ultimately starting my graph. From here, I need to go over 1 in both directions, but instead of going up, I've got to go down, and I've got to go down twice as fast. So instead of down 1, I'm going to go down 2 to get my first kind of symmetric pair of coordinates that are on each side of the vertex. That's kind of the worst of it right there. Once you have those down, if you know the pattern, you're just taking it maybe 1 or 2 more steps further to get a nice set of clustered coordinates to work through. The next one that I'm going to do is over 1 and then down 6 units instead of down 3 units. So I go down 1, 2, 3, 4, 5, 6. And then I've got enough coordinates here to get a pretty good idea about the shape of the graph. And we're pretty much set. What I'll point out on this guy is that the vertex is at this coordinate 1, 3. There's also an axis of symmetry here that's passing through that vertex, and that's at this value for x equals 1. So I always like tracking that. This is going to become a little more useful when you're trying to graph in, say, factored or standard form. In vertex form, it's really neither here nor there. We don't necessarily need it to help the process along. If I get this last guy where I see that I have, say, I'll do a different color. I'll probably do that like in green. Red would be a bad idea. I already got that one for my parent function. If I got this function and I see plus 2, I know my graph's going up 2 units. If I see plus 3, I've got to go counterintuitively left 3. All I'm really doing here is just kind of following the instructions. So I graph this. I've got my vertex, which is my starting point. If I don't have a number there for a, I want to think of the number that I could multiply x plus 3 squared by to not change it at all. And that's really just a 1. So when the a is not present, or when the a is 1, you followed the same pattern of behavior as you would for a parent function. You're going to get your vertex, you're going to go over up 1, and then you're going to go over up 3, and then over up 5. No real surprises here, no real curveballs. I think a lot of us are probably pretty comfortable with graphing these at this point, but I really like hammering on this just to kind of get comfortable with the pattern without using graphing calculators or Desmos or any assistive technology. It's something that we can kind of pick up and make the process much faster as we go. Vertex form, pretty straightforward. Not a whole lot of surprises. We can track down a vertex. We can track down an axis of symmetry. For this guy, it's at negative 3, 2 for the vertex. The axis of symmetry passes through that. It's the same thing as the x component of that coordinate. That kind of information is going to be more useful when I'm working with a format that's not necessarily set up in vertex form. And we're going to take a look at that here in just a second with a couple more examples on the next part of the notes. So let's say that I've got a quadratic. I want to graph it, but it's not in vertex form. So for example, here, right, maybe I've got x squared plus 6x plus 3, or I've got like negative 3x squared plus 12x minus 5. It's a lot more difficult to identify what the transformation template is in this sort of setup. We don't really have a form for that when there's like a 6x and an x squared flying around, right? I can maybe pick out what my y-interceptors are going to be. For this first function, if I plug in x equals 0 to find my y-intercept, I'm going to see that the only value that's left over is 3 because everything else just collapses to 0. You'll see something similar here for our other function where if you want the y-intercept where x is nothing, if you plug in x is 0 to this, the only thing that's left is this constant for negative 5. That's, at least right off the bat, all the information that I can get about how to graph these guys in standard. So it's not a terrifically useful format if I'm trying to graph. Maybe for solving, maybe for other contexts, but not graphing. So you've kind of got two options here. Option 1, if you want to graph these guys when they're in standard form, is going to be to complete the square and just change its format. If I want to complete the square on this, it's going to take me from standard form into vertex, which is going to be much easier to work with if I wanted to figure out the shape of its graph. So I'm going to practice that skill here. If I got my first function for y equals x squared plus 6x plus 3 is not likely to be the magic number that I need in order to have that to get it to factor perfectly. So I always move that right off the bat before I do anything just to get it out of the way. I move it over to the side with the y by subtracting it from both sides. And now what I'm left with is figuring out completing the square for x squared plus 6x plus something, right? So this is where that process of finding the magic number comes in. Completing the square is a very geometric argument. If you think about a square and you think about its area from geometry, I know that a square has all four sides congruent. So if I want the area of it inside that space, I know it's just s to the second, right? It's something times itself. It's the same thing here with the algebraic symbols. I want to break up my quadratic for x squared plus 6x in such a way that the side dimensions are exactly the same thing. So that it's like it times itself at the end of the day. If I focus on the x squared and what times itself is x to the second, I'm going to notice there that the first part of the side dimensions are x and x. But now I've got to take my 6x and I've got to split that up evenly to fit inside these rectangular regions. So if I've got 6x's that I've got to divide up evenly into those two spaces, I know that I'm going to need 3 of them and 3 of them in each of those little slots. So I'll write on the outside dimension that I have plus 3 and plus 3. The reason that it's just plus 3 on the outside is this is like an area model, right? So I'm multiplying rows and columns together. So x times 3 would get me plus 3x on the first part. Same thing on the other part. So now I'm just about done with the process. To find the magic number that I've got to add to my problem, I'm essentially taking those two constants values and I'm multiplying them together. I'm squaring it. So I'm going to do 3 times 3, which is positive 9. That's just the right number that I need to introduce to the problem to get the right side to factor perfectly into x plus 3 squared, which is going to help us get into vertex form. It's pretty much halfway done at that point. The only trick to this is that you can't just randomly add a number in an equation. Any of you guys who've got like younger siblings, or maybe if you were the younger sibling and you had an older sibling, or still have an older sibling, if they're young enough, if your parent gave you a treat or your sibling a treat, but not the other one, there was always a fight, right? That was always the case with me and my sister. So I always think about that in algebra. If I do something to one side of the equation, I got to do the same thing on the other side to keep it fair, to maintain the balance, right? So in this process of completing the square, you'll often see me write like a plus blank in the equation. I'm leaving that as a placeholder because I'm anticipating putting something there, and I do it on both sides to make sure that it's balanced. So over here with y minus 3, I'm also going to write that plus 9. If I put the minus 3 and the plus 9 together, I get y plus 6. All I've got to do now is just move the 6 to the other side, and we're in vertex form. So the final result of this process is going to tell me that I've got this quadratic in vertex form where it's x plus 3 squared and minus 6. That tells me that I'm going down 6 units and I'm going left 3 units to get the vertex. And because the a term is just a 1, I already know what the pattern of change is. So I'm going to go over 1, up 1. Then I'm going to go over 1, up 3. And then watch this. If I go over 1, up 5, I'm going to hit that y-intercept like I anticipated from standard form. So that's the graph of the red function by completing the square. You can get the y-intercept from standard, but that's kind of about it. What I want you to notice here on the vertex is that it's currently at -3, -6. The axis of symmetry is going to pass right through it. It's this vertical line that we write at x equals -3. The reason I keep harping on that is that completing the square is not necessarily the only way to get the graph if you're working with something in standard form. There's kind of a faster way to do it. And you may have noticed something when you were working from standard to vertex form. Anytime you're looking at the a term, from what you started with compared to what you got at the end, you'll notice that that never changes. It's always the same. So if I've got this other guy down here where I see like a -3 times x to the second, I know if I complete the square, when this is a tough one to do that with, my a term is still going to be -3. And that tells me a lot about the pattern of change, but I can't really glean anything else out from the process. The other thing that I want to point out here is if you take a look at, say, our value at which we're intersecting with the vertex. So in this graph in red, my vertex is at an x coordinate of -3. That's half of my b term if it was negative. If you take a look at this other quadratic where I see a plus 12x, if I take half of that, that's going to be 6. The negative version of that is going to be -6. So that might ultimately tell me that my vertex is somewhere at like -6 comma something. If I want to find that y value, I can just plug the x value back into the equation and evaluate it out. Now, I'm going to pause the video and complete the square here real fast off screen, just so you can see what this is going to be in vertex, and we can kind of illuminate that connection just a little bit further. All right. So off screen, I worked out completing the square here for this particular example. Again, this is not necessarily a trivial case. That a term being a -3 definitely throws a wrench in the works, and it requires a little creativity for how we're going to kind of manipulate that right-hand side, ultimately to work this out in the end. What you'll notice is that I added the 5 over to the other side immediately, and then I factored a -3 out of -3x squared plus 12x. I then completed the square inside of that set of parentheses where I did a +4. You'll notice on the other side of the equation, I didn't just write a +4 though. I wrote a -12. The reason that I did that is if I do like -3 times +4 in the parentheses, I haven't really created a +4 on the right-hand side. I've actually created a -12. So I've got to be really careful to get the right balance in the equation. So as I run that process out in vertex form, I get -3 times x minus 2 squared and then +7. Now, you may have noticed that in my earlier explanation, I said that I was going to take that b term, cut it in half, make it negative, and that was going to tell me where it's going to be. That would mean that my vertex is at like -6, but that's not necessarily true, right? Here, the vertex is actually going to be at 2 comma 7, which is nowhere near where I initially said it was going to be, right? So my initial intuition that I was doing like the -b over 2 is part of it. But notice that if I take into account the a term that's present, where I've got this -3, that's ultimately what's going to help build out the second way of doing this. So I made that mistake because I wasn't accounting for the right a term. If I want to figure out the axis of symmetry, the x component of where this vertex is going to go, I've got to take my b term in standard form and switch the sign. I've got to divide it by 2, but it's not just by 2. It's by 2a in this case. So if my a term is -3, twice that is -6. If I take, say, -12 divided by -6, that gets me the +2. That tells me where my axis of symmetry is, and then I've got half of where my vertex is supposed to be. Now, students will ask the question, how are you supposed to find the y-coordinate? That's all well and good that you figured out how far right you were going, but how far up are you going? Well, if you know the x component and you want to figure out the y component, you can just substitute that value back into your equation for standard form and see what you get as an output. What I mean by that is I got x equals 2. If I plug that back into my equation where I do -3 times 2 squared plus 12 times 2 minus 5, that gives me the 7. So there is another way to graph from standard form where you're not necessarily needing to complete the square. What it's going to rely on is making a recognition that this coordinate, at least the x component, is like half of the -b value but it's also being divided by the a term. So that's easier to do when a is 1. You can still do it when a is different. Some people are really big fans of this method because it allows them to completely sidestep completing the square. Some people are not fans of this method at all. Me personally, I'm comfortable with completing the square. I think it's a really interesting piece of math history, so I like practicing it and kind of playing with it. I very rarely use this other method, but that doesn't mean that it's a bad approach. It works really, really well, but it's kind of tricky to see like why it works. And as we go, when I come back after the subscon, I'll kind of like work this through with you guys maybe a couple more times and kind of explain it in greater detail. I just wanted to give some context as to why you're seeing that in the notes while I'm out. So if you notice that they kind of just throw that out there, it definitely feels like that. And we'll spend a bit more time kind of playing with it and exploring further why that happens. So that's what you can do when you're in standard form. Let's say that instead of in standard form, you're in factored form, and you want to figure out how to get a graph of this guy when all of a sudden you don't know where the vertex is, you don't know what the a term is, you don't even know where the y-intercept is going to go. You're just kind of stuck with this particular format. One way that you can potentially do this is to work your way back to standard or your way back to vertex form. And again, it's kind of personal preference which of those you might want to graph by. I'll call strategy 1 just get out of factored form. Here, factored form is nice for telling you like where the solutions of the function are. Those also happen to be the place where it's crossing the x-axis. That's why it's sometimes referred to as like intercept form. It's not, other than that, usually very good for helping us pin down where the vertex goes, what the transformations are, and how the pattern of change is. So for this first one, what I'll do is get out of factored form just by multiplying it together. So I'll take x plus 6 and I'll multiply it by x plus 2 and I'll just see what I get in standard form. So I'll get x squared, I'll get 6x, I'll get 2x, and I'll get 12. This is really ultimately the same thing as x squared plus 8x plus 12. So in standard form, I know where my y-intercept is. It's way up there at positive 12, which is way off the graph. That's about all I know. Now, that doesn't necessarily mean that I can't figure out what the graph's going to look like just from standard form. One thing that I can do in order to find the axis of symmetry is to say, okay, well, I've got to take my b value, I've got to make it negative, and I've got to divide it by 2 times a. So if my b value is 8, I'm doing negative 8 divided by 2 times 1. That means my axis of symmetry is going to be on this line, x equals negative 4. So it ultimately turns out that if I were to get this in vertex form, it's gone to the left 4 units. Now, that doesn't tell us the other part of the coordinate, right? That just tells us where the x coordinate is. If I want to figure out what the y coordinate is, I've got to take that x and I've got to plug it back into my equation. So what I'm going to do is run the calculation. Negative 4 squared plus 8 times negative 4, and then plus 12. I'm going to get a 16 minus a 32 plus 12. That's going to tell me the y value of the coordinate in this context. That's going to be like a negative 4 again. So I've got my vertex kind of down here in the lower left quadrant. Notice that in my standard form, my a term is just a 1. So I've got enough information here to apply the pattern for quadratics and figure out the shape of the graph from there. Now, what I want you to notice here is that once I finally sketch this guy out, there's 2 solutions or x-intercepts for the graph. There's one at x equals negative 6, and there's one at x equals negative 2. I could have figured that out from factored form if I think about what the y coordinate at those locations should be and solve it with something called the zero product property. If I take my equation and I set y equal to 0, so that I've got one thing times another equals nothing, the zero product property is almost like kind of an obvious but subtly really powerful math idea. The basic idea of it is if I tell you I'm thinking of 2 random numbers and I don't tell you what they are other than the fact that they multiply to 0, what can you be absolutely sure is true about at least one of them? One of them's nothing, right? Now, you don't know which one it is, So you're going to play it safe with the zero product property, and you're going to set each one equal to 0, and you're going to solve it. So when it's more complicated, instead of just two numbers, if I've got x plus 6 or I've got x plus 2, I'm still following the same idea where I set each of those to being nothing, but then I'm just solving it out. So I get a solution at x equals -2, and I get another one at -6. Those are the roots or the zeros or the x-intercepts from the graph. So factored form will tell you where you're crossing the x-axis, and pretty much that's it. You don't get a lot more information out of that in that particular case. You don't necessarily have to approach it by finding the axis of symmetry and then evaluating at that x to find the y. You could go even further and complete the square on that and get the vertex form out of it. That works totally fine. What I want you to notice is if you're trying to get the a term really fast, do x times x to get x squared and look at just that. That a term there is going to pop right out before you even get the rest of it in standard form. You can use a similar strategy here for this other one, where I've got like -2 times x plus 1 times x minus 3. I'm going to multiply this out to get it into standard form, but I'm not necessarily going to do the whole process. I'll do x plus 1 times x minus 3. X times x is going to get me x squared. Don't forget that there's going to be a -2 times the result of this area model. So really what this is going to look like is like -2x squared plus ... I know that that quadratic is going to open down twice as fast as usual. I can figure out where my solutions are going to be. If I've got x plus 1 times x minus 3 is equal to nothing, applying the zero product property is going to tell me that either x plus 1 is nothing or x minus 3 is nothing. I know that my solutions are x equals 3 and x equals -1. So I know where I'm crossing the x-axis. I know the graph is going down twice as fast as usual. Without formally getting into standard form, though, that's pretty much everything that I know. So what I'm going to do is just sort of jot down what I know so far. I've got a solution at x equals 3. I've got a solution at x equals -1. I want you to notice something on the red graph in terms of the distance that each of those solutions are from the axis of symmetry. If you take a look at like how far away this first solution at -6 is from the axis of symmetry, or how far away the other solution at -2 is from the axis of symmetry, they're the same difference, right? So that means the axis of symmetry is halfway between the span of the distance between the two roots or the two solutions. So you could go through all the trouble of getting this guy into standard form so that you could then complete the square to get it into vertex form and handle it that way. It works, it just takes a while. You could also go through the trouble of getting it into standard form, find the axis of symmetry, plug it into the function to find the rest of the vertex, and go from there. Also good. You could also make use of a pattern here where the axis of symmetry is at the halfway point between these two values. So if I think about my blue function where the distance between the two roots is 4 units, I go in 2 units from either side, and I know that my axis of symmetry for this is going to pass through this line x equals 1. Now, I'm not certain yet where the y coordinate of that is, but if I know that it's on this line x equals 1, I can just plug that back into my function, regardless of the form of it, and I can figure out the y coordinate by working it that way. So the second kind of way to do this when you're in factored form is to find the roots or the zeros or the solutions or the x-intercepts, and then find the halfway point in order to get halfway to your vertex by using the axis of symmetry. Some people really like this strategy. Some people don't like it at all. It's making use of the fact that quadratic graphs are symmetric by nature, and that's always going to be true no matter what quadratic you're working with. So the second strategy is going to tell me that x is 1 for the vertex. I'm going to plug that into maybe the factored form of the function to figure out what the corresponding y value is. So all I'm really doing is just substituting and simplifying. Here I'm going to have -2 times 2 times -1. That's the same thing as y equals 4. So my vertex is at 1 comma 4. My a term is -2. So I've got to go down. And I've got to go down twice as fast as usual. That's going to tell me that my graph is going to like pass through the x-axis at those locations. And it's going to give me a pretty good idea about the shape of the graph. My graph here is not sketched very good because I've got like a touch tablet at home that's really old and it's not like super effective, but it gives me a lot of information about the nature of the problem here. It tells me a lot of information about kind of the structure of things and how they're going and where it's going to end up. Again, there's lots of strategies to work with here. My expectation is not that you know how to do every single one. I want you to kind of work through some of these on your own and kind of come to your own conclusion. Is there a particular strategy that you really like? Are there particular strategies that you absolutely despise? Pick the ones that work for you and run them. We'll kind of practice a little bit of everything when I come back just to make sure that like everybody gets a chance to find a strategy that works for them and gets comfortable with it. There's a lot of interesting information here, right? If you get really stuck and there's just like too much stuff flying around, think about just getting back to vertex form. If you're in factored, go to standard, then complete the square to vertex. If you're in standard, go straight to complete the square, get to vertex. Everyone's doing pretty good with graphing from vertex based off of what I'm seeing from units 1 and 2. It's a very reliable way. Sometimes it takes a while, but it's not the only way. So I'll leave you with that. I think that's more than enough from the notes to kind of get you guys started. I want you guys to take some time to work through the practice for 3.2 with like a table partner or two, just to kind of put it into motion and get comfortable with it. If there's anything there that's feeling kind of wonky, if you got some lingering questions, or if there's anything that crops up that you want to take another look at, don't panic. Be more than happy to answer questions when I do come back to class. Otherwise, though, I'll see you guys next time. I hope you have a great rest of your day and take it easy.